Number 12. The thin signal. The recording sounds like a whistle, but nothing in the file proves that anything whistled. NOAA detected the signal in the Pacific in 1997 using its autonomous hydrophone array, a rising, narrow-band tone that seemed almost too clean to belong to a chaotic seafloor. It appeared once with enough clarity to earn a name, then disappeared before researchers could triangulate it. That leaves a contradiction at the center of the mystery. The sound is unusually distinct. The circumstances around it are unusually sparse. There is no confirmed creature, no visible eruption, and no complete public trail from detection to source. NOAA's later classification points toward volcanic activity, making the whistle less an impossible animal call than a probable geological event. But a probable category is not an address, and the missing address changes what the recording can tell us. The answer begins with how little was actually recorded. In July 1997, technicians at NOAA's Pacific Marine Environmental Laboratory were monitoring the Equatorial Pacific Ocean Autonomous Hydrophone Array. These instruments were designed to hear events that could cross enormous distances through the deep ocean sound channel: earthquakes, ice movement, volcanic tremor, and the low calls of animals too far away to see. Then one signal separated itself from the background. A thin line rose through the frequency range. On a spectrogram, it looked almost drawn by hand, a narrow-band upsweep, clean enough to suggest intention. To human ears, especially after processing, it resembles a whistle. But that resemblance is only a description of the sound. It does not identify a whistling animal, a machine, or anything with a mouth. The archive does not give us a complete investigation. It gives us a label, a date, a region, and a classification. The whistle. July 1997. Eastern Pacific. Unknown, but believed to be of volcanic origin. Why is there so little public information about a named NOAA mystery? The question is part of the mystery itself. The whistle became memorable because it was unusually recognizable, but the record surrounding it remained thin. There was no sequence of repeated detections like the bioduck, no seasonal pattern, no tagged animal producing a matching call, no mapped eruption site that closed the case. There was one clear acoustic fingerprint. Then the Pacific went quiet. The hydrophone array could tell researchers that the signal had traveled through the ocean. When enough stations detected the same event, researchers could compare arrival times and turn a distant sound into a location. The whistle did not provide enough of that chain. Without repeated arrivals, precise triangulation becomes difficult. Without a second recording, comparison becomes weaker. Without a visible event at the surface, the source remains below the water and beyond ordinary observation. You are listening from thousands of feet above a seafloor you cannot see. The signal is sharp. The origin is not. A tone climbs, vanishes, and leaves behind almost nothing that can be photographed. Underwater volcanoes do not produce one single sound. They can generate tremor, gas release, explosions, collapsing cavities, landslides, and pressure changes moving through rock and water. Some are broad and chaotic. Others can produce concentrated tones. The whistle's narrowband rise does not prove a particular eruption, but it keeps the signal within the range of geological events that can create a clean acoustic sweep. NOAA therefore placed it among sounds believed to have a volcanic origin. The wording is careful. It does not name a volcano or identify an eruption. The classification is a probability statement based on the signal's character and the behavior of known ocean processes. That explanation is less dramatic than a hidden animal, but it demands more physical accounting. A creature hypothesis can survive on resemblance alone. The sound feels like a call, so something must have called. A geological hypothesis has to account for the frequency, the rise, the distance, and the absence of a second recording. The source must be physically possible even when the event itself is gone. The whistle also differs from the louder mysteries recorded in the same era. The Bloop eventually found a plausible explanation in icequake activity, because its scale and structure matched known ice processes. Slowdown and Julia were associated with iceberg movement. The Western Pacific biotwang moved toward a biological explanation through later acoustic comparison. The whistle never received that second piece. It remained a single event with a likely category, but no exact address. That gap creates an operational risk. A clean, isolated tone can look intentional even when geology produced it. It can pull monitoring teams toward a biological or mechanical source, distort early classification, and send limited survey resources toward an explanation that the evidence cannot support. Troublingly, it shows how much of the ocean may be able to produce convincing, highly recognizable signals without leaving a visible trace. The clearer the sound, the easier it may be to overinterpret. A one-time recording can establish that a sound occurred. It cannot establish what produced it. The waveform is evidence of pressure moving through water, while the missing scene includes the seafloor, the surrounding water, and the event that shaped the signal. The name is memorable. The metadata is not. With no confirmed eruption or animal match, later descriptions naturally grew larger than the original evidence. The whistle became mysterious partly because the recording was so small. A huge ocean can carry a narrow signal across great distances, but distance strips away context. By the time the sound reaches a hydrophone, the instrument may preserve the event's shape while losing the details that explain it. The ocean keeps the trace and hides the scene. Proof would require more than the original waveform. A second detection from another station, a location consistent with the arrival times, a seasonal or repeated pattern, a seafloor event recorded by seismic instruments, sonar, or cameras, or a physical process capable of generating the same narrow-band upsweep. One clue can suggest a source. Several independent clues can constrain one. The whistle's sparse record is still useful. It gives researchers a baseline. One rare signal, one narrow frequency pattern, one proposed geological category, and no confirmed origin. Future detections can be compared against it, but the comparison may also expose the same weakness. A recognizable tone can arrive first, while the evidence needed to interpret it never follows. The whistle was never a confirmed creature call. It was never a documented eruption. It was a thin acoustic record that survived after the event itself had disappeared. For now, the signal identifies only one thing with certainty. A sound passed through the Pacific. The next clean signal may arrive with the same missing evidence, leaving researchers to decide whether recognition is a clue or the beginning of the mistake. Number 11. Rails underwater. What sounds like a train when there are no tracks, no engines, and no land for hundreds of miles? On March 5, 1997, NOAA's Pacific Marine Environmental Laboratory was listening to the equatorial Pacific through an autonomous hydrophone array. No ship was sitting above the source. No diver was close enough to hear it. No human being witnessed the event itself. The first evidence was a trace moving across a spectrogram, a narrow tone that rose in pitch, then settled into something almost steady. In the lab, that shape sounded familiar, a distant horn, wheels finding rhythm on rails. The analysts called it the train. The nickname described the impression, not the cause. The hydrophone had captured a machine sound from a place with no machines. The Pacific was already full of sounds that arrived without a visible scene. In the 1990s, NOAA's hydroacoustic stations recorded signals later known as the Bloop, Julia, Slow Down, Upsweep, and Whistle. Some were linked to moving ice. Some pointed toward geological activity. Others remained unresolved. But the train creates a sharper problem. Unlike cases supported by a later source identification or a distinctive pattern, its public evidence rests almost entirely on resemblance. A train horn normally comes with a location, tracks, a horizon, repeating wheels, a source that can be approached and inspected. The train had none of these. It crossed the water as a low-frequency signal, carried through the deep ocean sound channel, where sound can travel extraordinary distances before fading. By the time it reached the hydrophone, the rising pitch and sustained note survived. The source did not. At that moment, the analysts could establish that acoustic energy had reached the array. They could describe its frequency, timing, and shape. They could not establish whether the event began with a vessel, an animal, a landslide, or ice. A familiar pattern made the anomaly easier to name, but naming it did not make the source traceable. One possibility is ice. Icebergs can generate powerful underwater signals when they fracture, rotate, or scrape along the ocean floor. The contact is not silent. A massive block moving through seawater can create pressure waves that travel far beyond the visible ice. If it grounds on a ridge or drags across sediment, the tone may change with the length of the contact, the speed of the movement, and the geometry of the seafloor. That could explain why a natural event sounds mechanical. Friction produces rhythm. A long scrape can create a rising frequency as the contact changes. A resonant cavity in the ice can add a sustained tone. From a distance, the ocean can turn broken ice into something that resembles an engineered machine. But the recording could not prove that sequence. No tagged animal produced the same call. No repeated seasonal pattern closed the gap. No second piece of evidence placed an iceberg at the exact source. Ice movement was physically plausible, but plausibility was not identification. The distinction mattered because a plausible explanation could still send investigators toward the wrong part of the ocean. The location created another complication. An autonomous hydrophone array in the equatorial Pacific is designed to hear across great distances, not to sit directly over every event. Sound detected at one station tells researchers that acoustic energy arrived there. It does not automatically reveal where that energy began. With several stations, arrival time differences can narrow the source. With one incomplete record, the source may remain a broad region, or less than that. That gap changes the stakes. If the train were assigned to a ship, investigators might search for a vessel, logbook, or mechanical failure. If it were assigned to ice, they might look for drift paths, grounding events, or satellite evidence. A wrong attribution would not merely create a bad caption. It would erase the real event from the search, leaving an untraceable zone where the sound began and making the pattern itself stand in for proof. You are inside the recording now. There is no visible train, no rails beneath the waves. Only a tone climbing through the dark, steady enough to suggest intention, mechanical enough to suggest design. The water offers no explanation. It carries the signal while leaving the investigators with a shape and a decision. Treat the resemblance as a clue, or let it become a conclusion. The train belongs in the same conversation as other unexplained ocean sounds, but that comparison exposes its weakness. The Bloop, Julia, Slow Down, Upsweep, and Whistle each invited a different line of inquiry through their power, direction, duration, or later interpretation. The train offers fewer handles. Its identity rests almost entirely on what it sounds like. Resemblance can mislead. A whale call may resemble a siren. A volcanic tremor may resemble machinery. Ice can sound like metal because both can create repeating pressure changes. Ear recognizes a pattern before the evidence identifies an object. That helps researchers notice an anomaly. It becomes dangerous when the nickname turns into the explanation, because every later detail is then judged against the imagined train instead of against competing sources. The most plausible non-human mechanism is not a hidden railway beneath the Pacific. It is moving ice, a large piece fracturing, rotating, or scraping against the seafloor, with the ocean carrying the resulting tone through the deep sound channel. Yet that explanation remains a model, not a recovered scene. The recording shows what arrived at the hydrophone, not what happened where the sound began. So what else in the hydrophone archive may be only a convincing resemblance? And when the next machine sound rises from the deep, how quickly will a familiar pattern be mistaken for evidence before anyone can locate what made it? Number 10. The quack that moved. The ridiculous noise that hit a whale. On February 19, 2013, researchers in Wilhelmina Bay, off the western Antarctic peninsula, lowered instruments toward Antarctic minke whales moving through the cold water. The animals were difficult to see. Pack ice closed around them. They surfaced briefly. Most of the ocean remained hidden beneath a flat, white horizon. But the sound was easy to find. For decades, submarine operators and oceanographers had heard a repeating pulse in southern hemisphere waters. It sounded like a mechanical duck, a short quack, then another, about every 3.1 seconds. The signal sat low in the water, between roughly 50 and 300 hertz. It appeared often enough to become familiar, but not often enough to become explainable. That was the trap. A repeating sound starts to feel intentional. One that travels across an ocean basin starts to feel enormous. The hydrophones recorded only pressure moving through seawater. They did not show the source. They gave researchers a pattern, a season, and a direction. The animal itself remained missing. That missing animal mattered. The bioduck had been detected for years, especially during the Antarctic winter, when direct observation was hardest. Ships could not simply follow a brief pulse through pack ice. A visual survey might find a whale, but not necessarily the whale making that exact call. A distant hydrophone could hear the signal, but it could not put a face to it. The gap lasted for decades. The first detections entered the acoustic record long before biology could claim them. This was not one strange recording. It was the same unexplained event surviving repeated observation. Sound can cross an ocean basin before anyone sees its source. What counts as proof of what made it? In Wilhelmina Bay, the researchers tried to shrink the distance between sound and animal. They placed suction cup acoustic tags on individual Antarctic minke whales. The tags traveled with the animals, recording the underwater world from each whale's body. You are no longer listening from a distant hydrophone on the seafloor. You are beside the animal. The water is dark. The tag moves through every turn and dive. Then the pulse appears. Quack, another pulse. Quack. The same mechanical rhythm that had filled old recordings was captured at close range, on equipment attached directly to Antarctic minke whales. The evidence now had a physical source. The sound was no longer just a Southern Ocean signal with an animal-like quality. It had been recorded in the presence of identified animals, by instruments riding on individual whales. Researchers did not have to infer the source from a dramatic waveform. They could tie it to a living body. In 2014, Denise Risch and her colleagues published the result in Biology Letters. The bioduck was the vocalization of the Antarctic minke whale, Balaenoptera bonarensis. It was not machinery, shifting ice, or an unknown creature hiding beneath the Southern Ocean. It was a whale. The name survived because the sound was absurdly unlike the animal people imagined. Antarctic minke whales are compact baleen whales, built for cold water and broken ice. They are not monsters from the deepest trenches. They slip between flows, surface for seconds, and disappear before a camera is ready. Paul had been traveling through the ocean like a piece of equipment left running in an empty room. The tag recordings did more than identify the caller. They turned older detections into biological clues. If the signal appeared in a region during a particular season, researchers could treat it as evidence that Antarctic minke whales were nearby, even when ships could not see them. The sound that had concealed the animal could now help track it. Identification did not solve everything. The 2014 study connected the bioduck to Antarctic minke whales. It did not prove exactly what the call meant. The sound might be involved in contact between animals. It might relate to breeding behavior, movement, or conditions beneath the ice. The caller was known. The conversation was not. That distinction is easy to miss. Once a name is attached to a sound, the mystery appears finished. The source and the purpose are separate questions. Which animal made the signal? Why did it make it? Why did the call appear so consistently in recordings separated by thousands of miles and many years? The official record now reads neatly: a repeating low-frequency sound, first treated as an unidentified Southern Ocean signal, later attributed to Antarctic minke whales through acoustic tags deployed in Antarctic waters. The proof arrived much later than the sound. Researchers did not chase one perfect waveform to its source. They waited until the right animal carried the microphone into the right place. Then the old duck appeared beside it. The bioduck was never a machine in the ice. It was an Antarctic minke whale, tagged in Wilhelmina Bay in February 2013, carrying the answer on its back. Number 9. The seasonal pulse. In August 1991, engineers at NOAA's Pacific Marine Environmental Laboratory watched a line of sound rise across their hydrophone records. It began low, climbed through the frequency band over several seconds, and returned again. Not a boom, not a crack. A pulse with a slope. The signal appeared in the equatorial Pacific, where underwater listening systems were already recording distant earthquakes, ice movement, ships, and whales. This one kept returning on schedule. Analysts gave it a practical name: Upsweep. Start with the timing. Upsweep was strongest in spring and autumn. Its intensity changed, but the seasonal pattern held. A random fracture does not keep an appointment. A passing ship does not reappear in the same part of the year for more than a decade. The problem was not only what could make a sound like this. It was why the oceans seemed to make it seasonally. The waveform gave the next clue. Upsweep consisted of narrowband sounds, each lasting several seconds, with a frequency that rose as the signal continued. roughly 50 hertz to 100 hertz, low enough to travel through the deep Pacific, structured enough to stand apart from ordinary background noise. That shape mattered. A single sharp event gives you an instant, the moment something breaks, explodes, collapses, or strikes the seafloor. Upsweep gave analysts motion. The frequency climbed while the sound was still happening, as if the source itself were changing speed, pressure, or resonance. The Pacific did not produce one upsweep. It produced a train of them. For years, autonomous hydrophones logged repeated sequences. Signal could be detected across much of the Pacific basin. That meant the original source was powerful, persistent, or both. Distance created a problem. Sound could cross an ocean while the evidence at its origin disappeared into darkness, pressure, and moving water. A sound can cross an ocean basin before anyone sees its source. Then proof becomes difficult. For Upsweep, the first solid clue was repetition. This was not one strange recording that might be dismissed as equipment noise. It had a contour, a season, and a history. Repetition narrowed the field, but it did not close it. A whale can call repeatedly. Ice can fracture in patterns linked to season. Human machinery can operate on a schedule. Volcanic systems can pulse, tremble, and change as magma, gas, and seawater move through the crust. Each possibility explained part of the record. None explained all of it. PMEL analysts placed the probable source near 54 degrees south, 140 degrees west, in the South Pacific. That region lies far from busy coastlines, near submarine volcanic terrain where the seafloor is being built, cracked, heated, and reshaped. The location did not reveal a smoking crater waiting for a camera. It gave scientists something more useful and more frustrating: a geographic constraint. A signal arriving at several listening stations can be compared for timing. Differences in arrival time let researchers estimate where the sound began. But the ocean is not an empty room. Temperature layers bend sound. Depth changes its path. Reflections blur the arrival. A source can be localized without being directly observed. The leading explanation became geological. Sweep may have come from volcanic activity. Hot fluids may have moved through cracks beneath the seafloor. Seawater may have entered a heated vent system and produced a resonant flow. The rising tone may have reflected a changing cavity, pressure field, or discharge rate. Those are not interchangeable ideas. Volcanic names a family of processes, not one machine inside the Earth. An eruption, a hydrothermal vent, a gas release, and a tremor can all belong to the same geological setting, while producing very different sounds. That is why Upsweep remained unresolved even after its probable region was identified. The record suggested a process. It did not provide the final mechanism. The seasonal pulse made the puzzle sharper. If the spring and autumn peaks reflected volcanic or hydrothermal behavior, then something in the system was responding to a yearly change. Ocean pressure, temperature, tidal forcing, fractures opening and closing. Water moving through hot rock as the surrounding environment changed. The rhythm might come from the source itself, or from the way the ocean carried the sound. You are listening from thousands of miles away. The waveform rises, fades, and rises again. Somewhere beneath the surface, the source is hidden by water and distance. No photograph arrives. No animal breaks the surface. Only the timing remains. By the 2000s, Upsweep had weakened. The decline did not turn it into a solved event. It made the record stranger. A signal strong enough to cross the Pacific was becoming quieter, but it had not cleanly vanished. Whatever produced it was changing. Shift fits a geological system losing energy, changing its flow, or moving away from the conditions that made the sound detectable. It fits volcanic or hydrothermal activity. But fit is not identification. The cleanest conclusion stays narrow. Upsweep was a recurring, narrow-band, rising frequency signal first detected by PMEL in 1991. It peaked seasonally, came from a probable volcanic region of the South Pacific, and declined over time. The leading explanation is geological noise linked to volcanic or hydrothermal activity. The exact source process remains unconfirmed. The seasonal rhythm does not point to a creature waiting below the hydrophones. It points to an active part of the Earth, where fluids, heat, pressure, and fractured rock may have turned into sound. The last record is quieter than the first. The rise is still there, stretched across the graph. Somewhere near 54 degrees south, 140 degrees west, the seabed moves beneath the water. The hydrophone catches the note climbing once more. By the time anyone could reach the source, it is already gone. Number 8. The loneliest frequency. By the time anyone could reach the source, it was already gone. Now picture the opposite kind of mystery. Not a sound swallowed by geology, but a voice that kept returning. Year after year, season after season. Same ocean, same narrow band on the graph, still no body. In 1989, somewhere in the U.S. Navy's North Pacific hydrophone record, a whale-like call appeared that did not fit. It was not blue whale low, not fin whale low. It was higher, sharper, centered near 51.75 hertz, usually rounded to 52. That number sounds small until you hear what it means. In the deep ocean, frequency works like identity. A few dozen hertz can separate one of the largest animals on Earth from another. After the Cold War, pieces of the SOSIS acoustic archive opened to civilian researchers. At Woods Hole Oceanographic Institution, William A. Watkins began following that odd call through the Pacific. From 1992 onward, Watkins and colleagues tracked it on spectrograms and bearings alone. No photograph, no biopsy dart, no tag. Just a moving source, heard across basin-scale distance by instruments built for submarines and later used for science. That is where the campfire story begins. Was the whale truly alone? When the signal reached the public, people did what they often do with a disembodied voice. They gave it a life. Then they gave it a wound. The animal became the loneliest whale, one impossible singer calling at the wrong frequency, unheard by its own kind. It is a beautiful story. The data are messier. Watkins's team was doing something colder and harder. In 2004, William A. Watkins, Marianne Daher, Joseph E. George, David Rodriguez, Nancy A. Marzio, and Daniel P. Gannon published a 12-year record covering 1992 to 2004. Their animal crossed the North Pacific on routes broadly consistent with migration. It moved between lower latitudes and waters nearer the Aleutians and Gulf of Alaska. The pattern looked biological. The sound did too. The call itself sat in an awkward place. Blue whales often call far lower, roughly 10 to 39 hertz depending on population and call type. Fin whales are famous for calls around 20 hertz. This one kept landing near 52. That made it unusual. Unusual is not the same as solitary. Sit with the researchers instead of the mythmakers, and the strange part changes. Not a tragic cartoon of a whale crying into emptiness. A limit in the instruments. SOSIS could hear across enormous distances and estimate direction. It could tell you that something was there and moving. But hearing a sound across an ocean basin is not the same as meeting its source. Here, proof stopped at repeat detection. It never became a face. Somewhere inside that gap, the name stuck. People turned a voice into a ghost story. The so-called 52 hertz whale. Once that label took hold, emotion rushed in to fill every missing piece. A different frequency became proof that other whales could not hear it. No identification became proof there was only one. A persistent signal became a permanent exile, moving through cold water under a sky no one could see from below. The image is powerful because it turns an acoustic anomaly into a character. But whale hearing is broader than the legend allows. A mismatched frequency does not prove total isolation. Large whales do not live inside one perfect note like a lock and key. Produce different call types. Populations drift. Frequencies change over decades. Hybrids exist. Undersampled groups exist. Later reports of 52 hertz-like detections make the neat myth even shakier. The moment similar calls appear elsewhere, the fairy tale of one doomed singer starts to fray. The original record remains real. The picture just gets narrower. What is documented is strong. First noticed in 1989, followed systematically from 1992, published after 12 years of tracking. Detected across the North Pacific in a pattern broadly consistent with a migrating whale. Never visually confirmed, never genetically sampled, never tied to a known species with certainty. That is a remarkable acoustic record. It is also exactly the kind of record that pulls people past the edge of the evidence. You can feel why. A hidden volcanic source is impersonal. Ice scraping is impersonal. A recurring call from an unidentified whale-like source lands differently. It sounds close to language even when it is not. It feels like intention, even when all you really have is repetition. The ocean gives you a line on a spectrogram. The human brain supplies loneliness, grief, and a whole private biography for an animal no one has ever seen. The harder reading is less cinematic. The 52 Hz signal may have come from one abnormal individual, or a hybrid, or an unknown call type from a known species, or more than one animal producing similar high-frequency calls. The acoustic record cannot cleanly choose between them. The very thing that made the sound famous, its ability to travel, also kept the source far away. The ocean carried the call farther than the science could carry certainty. Was the whale alone? The honest answer is that the record does not know. It knows there was a recurring whale-like call near 52 Hz. It knows researchers could follow it over years. It knows the source did not fit the standard catalog cleanly. The saddest part of the story, the part people remember first, came later. Out in the North Pacific, the hydrophones did not hear a legend. They heard a frequency. A narrow, persistent, slightly misplaced voice moving through black water beyond the reach of eyes. Whether one whale made it or several, whether it was unusual or merely understudied, the loneliness was the human invention. The anomaly was real. The exile was not. A thin line near 52 Hz kept crossing the dark and left no shape behind it. Number 7. The falling note. The note sounds like something enormous dying. On May 19, 1997, NOAA's Pacific Hydrophone Network captured it far from any eyewitness, far from any camera, and thousands of kilometers from the Antarctic ice that may have produced it. The signal lasted roughly 7 minutes. Its pitch did not hold. It fell slowly and continuously, as though a massive body were dragging itself downward through the dark. The recording arrived after another unseen voice had already crossed the Pacific and acquired a human story. This one offered no loneliness, no recognizable call, and no repeated pattern that could be assigned to an animal. It was a mechanical descent, a tone losing height in real time. The physical question is simple. What event can make a sound fall for minutes? The instrument that heard it was not sitting beside an iceberg. NOAA's autonomous hydrophone array operated in the equatorial Pacific. It was designed to listen for low-frequency sound moving through the ocean. These systems grew out of the same acoustic world as Cold War submarine surveillance, but their scientific targets had expanded to whales, earthquakes, volcanic activity, ice, and signals with no immediate name. The distance makes the mystery harder to read. A microphone beside breaking ice might record a sharp crack, a burst of grinding, or the collapse of a nearby surface. A hydrophone a basin away receives something filtered by the ocean itself. Water removes some frequencies, carries others, and turns a local event into a long, altered trace. The signal NOAA, labeled "slow down," was not a single impact. It was a gradual downward sweep. The public version is often sped up because, at its original low frequency, the change is difficult for human ears to appreciate. Processed for listening, it resembles a falling moan. Something begins high, then sinks. It does not end with an explosion. It keeps descending until the recording releases it. Pitch carries information about motion, scale, and changing physical conditions. A whale can shift the frequency of a call. A machine can change speed. A volcanic system can produce pulses as pressure moves through rock. The shape of this signal suggested a process unfolding over time, not a creature choosing to sing one very long note. The source was placed broadly in the far southern oceanic sector, often retold as waters near Antarctica and the Antarctic Peninsula. The public record does not provide the clean scene people want. One named iceberg, one exact coordinate, or one visible calving front caught at the instant of failure. No photograph shows the source beside the waveform. There is only the sound, the network that detected it, and the physics that followed. In the ocean, low-frequency energy can travel through the SOFAR channel, a layer that acts like a natural acoustic corridor. Sound can remain trapped there and move across thousands of kilometers with surprisingly little loss. An event near Antarctic ice can reach a Pacific hydrophone without announcing itself locally. The signal arrives after crossing water, weather, and time. You are nowhere near the ice. The hydrophone hangs below the surface, silent except for pressure changes moving through the ocean. Then the line begins to bend downward. No surface disturbance is visible. No animal rises. Somewhere beyond the horizon, a body large enough to reshape its surroundings may be sliding, cracking, or coming free. The recording became less monstrous and more difficult to explain. NOAA. Researchers associated slowdown with ice-related seismic or acoustic activity, especially the movement of a large iceberg. The proposed mechanisms are ordinary only in name. An iceberg can ground against the seafloor and scrape across sediment. It can fracture under stress. It can calve, shift, or grind against another mass of ice. Each motion converts enormous mechanical force into sound. The falling note could come from friction changing as the contact surface moves. Imagine a heavy block dragged across a rough floor. At first, resistance is high. Then the contact changes. The speed alters. The resonant frequency drops. In Antarctic waters, the block is not a machine part. It is a floating mass of ice interacting with the seafloor, a glacier or another iceberg over a distance measured in hundreds of meters. The result is not a monster calling from below. It is a continent-scale object failing under pressure. The explanation does not make the recording simple. The exact event remains unresolved. Was the source a grounding iceberg, a calving front, or a fracture propagating through thick ice? Could scraping and cracking have combined inside the ocean's deepest acoustic pathway? The broad category is much stronger than the local address. That distinction disappears easily when a nickname becomes a legend. Slow down sounds like a description of intention, as if the thing itself were slowing down. It came from the acoustic behavior. The frequency decreased gradually over the recording. The title is not evidence of an animal, a machine, or a dying body. It is a label attached to a shape. A shape can mislead when the source is far away. A signal that crosses an ocean basin before anyone sees its origin creates a severe evidentiary problem. The hydrophone proves that pressure changed at the receiver. It can help establish direction and timing. It can compare the signal with known signatures. It cannot automatically identify the object that moved thousands of kilometers away. The original mystery narrowed without disappearing. NOAA no longer treats slow down as an unexplained biological call. The useful question is, which ice event produced this particular descent and where exactly it happened? Ice friction provides the missing mechanism. As a massive iceberg drags or grinds against the ocean floor, the contact keeps changing. Pressure builds. A section slips. Resistance shifts. The vibration moves downward. Cracking and calving can add their own energy, but the long falling signature comes from a process changing its grip. The sound was not a voice. It was a moving boundary between ice, rock, and water. On the hydrophone record, that boundary keeps descending for 7 minutes. The source remains outside the frame. Water carries the note northward. The frequency falls. Somewhere near the Antarctic Peninsula, an unseen mass shifts against the seafloor. Then the tone drops again, and the recording cuts off before the ice does. Number 6. The living engine. At 20 Hz, the ocean does not sound alive. It sounds engineered. A pulse appears, then another, then another. Each one arrives with such stubborn regularity that the spectrogram begins to resemble a machine running somewhere beyond the horizon. The source is invisible. The rhythm is not. The animal that sounded like a hidden engine. During the late Cold War, and later in civilian recordings made from former Navy hydrophones, analysts kept finding these low-frequency trains moving through the North Pacific. Long sequences. Repeated pulses. Some were strong enough to travel across basin-scale distances. The obvious explanations were human. A distant ship, industrial equipment, seismic instruments, some piece of machinery working below the surface. But the signal had no visible factory, no engine room, no drilling platform. Only a pattern marching across the record. A pulse that feels industrial creates a specific problem. Machines make repetition seem natural. Biology is expected to be irregular, breathy, and difficult to confuse with infrastructure. Fin whale calls sit in exactly the part of the ocean where human technology is loudest. Around 20 Hz, a whale is calling near the lower edge of human hearing, in the same acoustic neighborhood as ship traffic, seismic activity, volcanic tremor, and ice. The first clue was not what the sound resembled. It was the acoustic range that created the resemblance. Fin whales are the second largest whale species on Earth. An adult can reach about 85 feet and weigh up to 80 tons. Size alone does not explain the illusion. The crucial detail is the song. Male fin whales produce powerful, stereotyped pulses arranged into repeated sequences. They do not need to sound dramatic, they need to remain consistent. One pulse sounds like an animal. A long train of pulses begins to look like a system. On a hydrophone, the waveform arrives stripped of everything that would identify its maker at the surface. No silhouette, no breath, no fluke, no sense of scale, only pressure changes traveling through water. The receiver knows that something moved the ocean. It cannot tell whether the source had steel walls or skin. That distinction became especially important in the 1990s, when NOAA's Pacific Marine Environmental Laboratory and other researchers began using long-range acoustic systems to study the ocean. The SOSUS network had been built for military surveillance, but its hydrophones could hear far more than submarines. They detected earthquakes, ice, ships, and whales. The same infrastructure that once searched for hidden machines was revealing a living one. Fin whale pulse trains became some of the clearest biological signatures in the recordings. They were not loud in the way a nearby explosion is loud. Their low frequencies propagated efficiently through seawater. A call produced in one region could reach instruments far away. The ocean turned a whale into a distributed signal. That created another trap. A signal traveling hundreds or thousands of miles loses its local context. The hydrophone may detect the pulse long after the whale has moved on. Several stations can help establish timing and direction, but a single receiver sees only the arrival. The sound has crossed an ocean before anyone has seen its source. The central question is difficult for a simple reason. If a sound can cross an ocean basin before anyone sees what made it, what counts as proof? For fin whales, the answer did not come from one spectacular recording. It came from accumulation. Researchers compared pulse timing, frequency, geography, season, and repeated detections. In the North Pacific, autonomous hydrophones recorded fin whale calls over basin-scale distances. The patterns were not random noise. They clustered by region and changed with the seasons. Different populations produced different timing and song structures. The machine-like rhythm was becoming a biological map. A pulse train heard in one part of the Pacific could be compared with calls detected elsewhere. If the timing matched, the signal appeared during the expected breeding season, and multiple hydrophones placed it within a plausible range, the industrial explanation weakened. Machinery could make the sound. It would not migrate, repeat a population-specific song, or appear across the same seasonal acoustic network. The rhythm itself carried the evidence. There is something almost unfair about the fin whale's voice. The animal is enormous, but the sound reaching a distant recorder may be reduced to a thin, orderly pattern. To human ears, a sped-up version can become a strange tone. On the original recording, it is slower and lower, a sequence of pressure pulses sitting just above or near the boundary of what people can hear. You are listening to a living engine, but the engine has no metal parts. Its power comes from the whale's body, its repeated song, and the water column carrying the signal outward. Fusion was not a single famous mystery with one dramatic reveal. It was a recurring analytical problem. Patterned whale calls were filed mentally beside machinery because the pattern looked too clean to be biological. The nickname industrial described the listener's first impression, not the source. The signal itself was never evidence of a hidden factory. The evidence appeared when the sound stopped being treated as an isolated waveform. Frequency explained why the call occupied an industrial acoustic neighborhood. Rhythm explained why it looked mechanical. Propagation explained why it could appear at remote hydrophones without a nearby whale. Season and geography supplied the missing location. Repeated detections turned an anonymous pulse into the signature of a population. Officially, the record could be described as low-frequency acoustic energy detected by hydrophones. In reality, it was an 80-ton animal sending a patterned pulse through the Pacific. The hidden engine was still moving when the spectrogram ended. Number 5. The trench call. A call near the Mariana Trench began with a document, not a sighting. In 2014, NOAA and Oregon State University researchers placed passive acoustic recorders in the western Pacific, near the Mariana Archipelago. The instruments listened in one of the deepest and least observed regions on Earth. No camera pointed toward the source. No tagged animal followed it. Microphones hung in the water, waiting for pressure changes to arrive. Then the recorders captured a sound lasting roughly 3 seconds. It began low, a pulse. Then another layer rose through it, climbing toward a sharp, metallic ending. The 5-part call seemed to bend from whale song toward machinery. Its frequency stretched from about 38 hertz to nearly 8 kilohertz, an unusually broad range for a sound associated with a baleen whale. That breadth mattered. Low frequencies can travel across vast distances, while higher components can be distorted by depth, temperature, and equipment. Together, they could identify an animal, or make a biological call resemble a mechanical signal, and send researchers toward the wrong source. The researchers gave it a name that admitted exactly how little they knew: the Western Pacific Biotwang. Bio because something living seemed likely. Twang because the final note sounded like metal struck underwater. The location made the sound larger than the recording itself. The Mariana Trench is not merely deep, it is mythologized. A signal from its vicinity carries the weight of everything people imagine below the surface: pressure, darkness, creatures no one has filmed, and distances too great for an easy answer. If the source were a whale, it could cross an ocean basin before anyone saw it. If the source were artificial, an entire biological interpretation could be built on underwater noise. The first clue was not depth, it was resemblance. In 2016, Sharon Newkirk and her colleagues compared the biotwang with a strange call recorded from dwarf minke whales near Australia's Great Barrier Reef. Those whales were known for a vocalization nicknamed the Star Wars call, a rising synthetic sound with the same science fiction edge. The Western Pacific recording was not identical. Its acoustic shape was close enough to make minke whales a serious candidate. Not a monster, not a machine. A whale hypothesis built from sound alone. Resemblance was not identification. A similar voice can belong to a different animal, especially across different oceans. Misidentifying the species would do more than create a wrong label. It could merge two populations in the records and make their movements appear to belong to one animal. The original researchers had no visual confirmation, no whale surface beside the recorder. No tag transmitted the call from a known individual. The biotwang remained probable, not proven. The call appeared repeatedly in acoustic archives, separated by distance and time. It was not one corrupted burst, it was a pattern. That changed the question. Instead of asking only what could make the sound, researchers could ask whether it marked a route, a season, or a population that surveys were failing to see. NOAA researchers turned to a much larger archive. Rather than listening manually to every hour of underwater sound, they trained machine learning systems to search for the biotwang's distinctive shape. The software scanned years of recordings across the western and central North Pacific. It looked for the same low beginning, rising middle, and metallic final note. The question moved beyond what could make the sound. Researchers asked where it appeared and what was moving through those waters at the same time. If the detections mapped a migration route, they could reveal habitat outside the reach of ships. If they did not, the apparent pattern might be an artifact of recording conditions, making sound alone another source of uncertainty. Later analysis found that biotwang detections overlapped with survey records of Bruda's whales. These tropical and subtropical baleen whales often travel offshore, surface unpredictably, and are difficult to study directly. No camera caught one producing the call. But when automated acoustic detections were placed beside visual sightings, the pattern lined up. The strange voice was following whales. That result raised the stakes. If the biotwang could track Bruda's whales, it might help monitor animals that spend much of their lives beyond visual surveys. But an acoustic map is not a census. A recorder can register a call without revealing how many animals made it, whether they were residents or travelers, or whether silent whales had passed nearby. A sound can expose an invisible route while still hiding the population using it. Not every detection came with a visible animal. The evidence was geographic and statistical. A call appeared in a region. Bruda's whales were documented there. The same relationship repeated across large acoustic datasets. Recurrence narrowed the possibilities, but it did not close the gap between association and proof. The Western Pacific biotwang became useful as more than a mystery. A sound first associated with minke whales because of its Star Wars resemblance began pointing toward Bruda's whales instead. The original comparison had identified a real acoustic similarity. Similar calls do not guarantee the same species. A whale's voice does not carry a species label in its waveform, and a monitoring program built on the wrong attribution could overlook a population while believing it was tracking another. The trench supplied the atmosphere. The archive supplied the evidence. You are listening to a signal recorded in darkness, far below ordinary observation. There is no image of the animal. No single hydrophone can show its exact position. Yet dozens of detections, spread across seasons and locations, begin to outline where an elusive whale population is moving. The setting encouraged a monster story. The metallic ending sharpened it. The source remained invisible. The recording also contained a quieter warning. The 5-part structure, the broad frequency range, the repeated appearances, and the overlap with Bruda's whale surveys all pointed toward biology. But each clue depended on context. Remove that context, and the ocean's machinery can sound alive, or a living migration can disappear into the noise. The Western Pacific biotwang may be a Bruda's whale call, but that uncertainty remains operational, not merely philosophical. Until a recorder, a sighting, or a tag connects the sound to an individual, researchers cannot know how many movements are being missed, or how many hidden whale populations are already waiting inside the archives. Number 4. Julia. The howl that made evidence feel personal. On March 1, 1999, NOAA hydrophones in the eastern equatorial Pacific captured a sound that seemed less like a signal and more like a voice calling from somewhere beyond the map. It lasted about 15 seconds. The sound rose, bent, and faded across the recording, as if something enormous had drawn breath beneath the ocean. The hydrophones were built for distance. Autonomous instruments spread through the Pacific, listening through water that can carry low-frequency sound across entire basins. They could detect an event hundreds or thousands of miles away, yet provide no photograph, no surface disturbance, and no clear point of origin. Julia arrived as sound without a body. When people heard a call that seemed almost human, the mind supplied what the instruments could not: a shape, a shadow, a creature large enough to make the water itself speak. Online retellings attached Julia to an alleged satellite image showing a vast, dark form beneath the surface. The image circulated as visual proof, presented as the thing NOAA had recorded. It was the perfect match for a mystery, which is exactly why it spread faster than the harder evidence. The sound itself was real. NOAA recorded it. Multiple hydrophones detected it. Its strange character did not depend on an invented photograph. The photograph supplied certainty, and certainty was exactly what the recording lacked. At first, Julia belonged to the public category of unidentified ocean sounds, dramatic, low-frequency signals not immediately matched to a ship, a whale, an earthquake, or a volcanic eruption. The name made the mystery portable. Technical trace became a character. The call had an identity before it had a source. A name can make an unknown thing feel more alive than it is. The signal's power came from physics. In the deep ocean, low-frequency sound can enter the SOFAR channel, a layer where changes in water temperature and pressure help guide acoustic energy over enormous distances. A sound produced in remote Antarctic waters can travel through that channel and arrive in the Pacific as a clean, eerie trace. By the time it reaches a hydrophone, the original scene may be thousands of miles away and already over. That distance is where false images become dangerous. The farther sound travels from the event that made it, the easier it becomes to attach the recording to the wrong scene and call the fit obvious. You are listening in darkness. The source is moving, scraping, breaking, or grinding somewhere beyond sight. The recording crosses the ocean before any observer reaches the place that made it. Sound can prove that something happened, while leaving just enough empty space for myth to rush in first. For Julia, the answer began with the shape of the signal and the environment around it. NOAA's Pacific Marine Environmental Laboratory later placed it among sounds consistent with Antarctic ice activity. The leading explanation is an iceberg running aground or scraping across the seafloor. A grounding event at that scale is violent physics. A mass of ice meeting resistance, pressure transferring into vibration, vibration entering deep water, and deep water carrying it outward like a broadcast. That explanation sounds less dramatic only because the word iceberg feels familiar. Scale is not familiar. An iceberg grounding can involve hundreds of meters of ice, immense pressure, and a seafloor strong enough to resist the impact. The resulting vibration does not need a living throat. It needs friction, weight, and a long acoustic pathway. The waveform's human-like quality was a trap. It encouraged listeners to hear intention inside a physical process. A rise in pitch became a cry. A descending contour became a warning. Compression and playback made the sound easier for human ears to follow, but they also made it feel closer to speech. The ocean produced a pattern. The audience turned that pattern into a speaker. Then the picture arrived and did something worse than decorate the story. It replaced the actual evidence hierarchy. Instead of starting with a timed recording, a propagation path, and a plausible physical source, audiences started with a dramatic silhouette and forced the sound to serve it. The viral satellite claim was attractive because it appeared to close every gap at once. The hydrophones had recorded a powerful sound. The alleged shadow provided a huge object. The story gained a source, a scale, and a face without requiring a confirmed location. But matching a satellite image to a hydrophone event is not a matter of resemblance. It requires a verified timestamp, a precise position, an identifiable physical event, and an acoustic path consistent with the water and seafloor between them. Without those links, a dark shape in an image can overwrite a stronger record with a weaker one simply because it is easier to imagine. The shadow stories supplied none of that. NOAA did not identify a specific named iceberg for March 1, 1999. It did not publish a precise grounding site tied to a matching satellite observation. The official explanation is a physical category, not a full reconstruction of the individual moment. That gap matters, but for the opposite reason myth prefers. In science, an incomplete chain limits the claim. In popular retellings, the same gap becomes permission to insert whatever image feels satisfying. Once that happens, the unsupported visual does more than mislead one story. It trains audiences to distrust the slower, less cinematic process that real data requires. A recording can establish that something happened. Multiple hydrophones can help estimate where it happened. Frequency, duration, propagation path, and environmental conditions can narrow what kind of event produced it. If a viral image gets accepted anyway, those measurements are pushed into the background, and the invented visual becomes the memory people keep. Julia became famous because it seemed to have a voice. The false image made that voice visible. It did not strengthen the case. It showed how quickly a genuine signal could recruit an invented body, and how easily the invented body could eclipse the signal that came first. The official explanation is not that Julia was trivial. It was ice, and ice on that scale can fracture, grind, and strike the seafloor with enough force to announce itself across an ocean basin. The sound was real. The remaining uncertainty lies in the missing specifics of one distant event, not in a hidden creature waiting inside a convenient picture. And that is the part that should linger. Julia is memorable because the audio survived while the scene itself remained out of reach. The false image stepped into that absence and stayed there long enough to become part of the legend. If one unsupported picture can do that to a well-documented NOAA recording, then Julia is not only a story about one eerie call in 1999. It is a warning about every other ocean sound that travels farther than direct observation. Every bad timestamp that hardens into lore. Every visual mismatch that reaches the public before verification does. The howl was real. The risk is how often the wrong image gets there first. Number 3. The singing volcano. In the early 2000s, NOAA's Pacific Marine Environmental Laboratory was listening across the South Pacific and catching signals that had traveled farther than sight ever could. One of them did not arrive as a bang. It arrived as a ladder. On a spectrogram, narrow bands stacked above each other in clean, almost musical lines. It is the kind of pattern that makes you stop and ask how a volcano can be heard before anyone sees it. Monowai Seamount sits in the Kermadec volcanic arc northeast of New Zealand. This is not some abyssal mystery buried in extreme depth. Its summit lies only about 100 meters below sea level. That shallow position lets unrest in the rock couple into the water above it with unnerving efficiency. A dramatic sound crossing an ocean basin is not proof by itself. Proof starts to form when the signal, the place, and the physics lock together. Now the signal. Not broadband like a crack, not the short punch of a single explosion. Harmonic tremor. Multiple narrow frequency bands ran nearly parallel on the display. They lasted long enough to imply a system staying excited, not one brief, violent release. This was not one event. It was something holding a note. That distinction matters. A ship can make tonal noise, but ships move and reveal themselves in other ways. An earthquake throws a different acoustic signature. A landslide can roar, but usually as a burst, not as a stable ladder of tones. Harmonic tremor points somewhere else. Resonance. Magma moving through a conduit. Gas release pulsing through fractured rock. Seawater interacting with a shallow eruptive system. Maybe one mechanism, maybe several at once. The shape of the sound narrows the suspect list. NOAA researchers had been collecting hydroacoustic data across the Pacific because low-frequency energy can enter the deep sound channel and travel enormous distances with surprisingly little loss. So the puzzle at Mauna Kea was not that a volcano made noise. Submarine volcanoes do that through eruptions, degassing, tremor, landslides, and hydrothermal activity. The puzzle was the form. Why this repeated tonal structure? Why something closer to sustained vibration than detonation? Mauna Kea is not a neat cone sitting still. It is one of the most active submarine volcanoes in the Tonga-Kermadec system, part of the plate boundary where the Pacific Plate descends beneath the Australian Plate. That setting feeds magma upward. It also builds a structure under constant stress. Cracks open, conduits clog, gas separates, pressure changes. The volcano does not need to erupt like a movie volcano to become acoustically loud. It only needs a cavity, a conduit, or a fracture network driven hard enough to ring. Start with the timing scale. Seconds would suggest a blast, minutes to hours suggest a process. Harmonic tremor belongs to the second category. It appears when the source keeps supplying energy. In air, you might call it a hum. Underwater, moving through rock and seawater together, it becomes a transmitted mechanical argument that something below stayed active longer than a single rupture should allow. Then the depth. About 100 meters below sea level is shallow for a submarine volcano. Pressure is high, but not so high that water completely suppresses every surface-coupled effect. Gas, magma, and water can interact in ways that make the system acoustically efficient. The volcano is close enough to the ocean above it to use that ocean as part of the instrument. Then the pattern. Harmonics mean repeated spacing. A fundamental tone plus overtones, or at least a source behaving as if resonance chambers and repeating pulses are involved. This does not prove one exact mechanism. It does show that randomness is a poor fit. When a sound crosses an ocean basin before anyone sees its source, structure inside the signal is the clue that matters. Hydrophones, though, can only take you so far. They can tell you that something happened. With multiple detections, they can help tell you where. They can suggest what family of event you are dealing with. They cannot, by themselves, show you a volcano physically rebuilding under the water. For a while, Mauna Kea sat in that uncomfortable space ocean acoustics often creates. A credible source, a distinctive signal, and a mechanism still argued over at the fine scale. Then the seafloor moved fast enough for ships to catch it in the act. In 2011, repeated bathymetric surveys mapped Mauna Kea's summit and flanks over just 5 days. 5. Not decades, not even a season. Between passes, parts of the volcano changed by up to about 18.8 meters vertically. A 6-story building had effectively appeared or collapsed on the seabed between one work week and the next. The estimated volume added in that short interval was about 8.75 million cubic meters of new volcanic material. Those numbers do more than say Mauna Kea is active. They show why a sustained hydroacoustic tremor from this place deserved serious attention. A volcano that can grow and fail on human timescales is exactly the kind of system that can keep forcing gas, magma, rock, and seawater into repeated vibration. The sound and the topography come from different instruments, but they begin to describe the same behavior. The scale shift matters too. An unexplained sound becomes less mysterious when geology arrives with measurements. Not less strange, more specific. The source is no longer an abstract dot on a triangulation map. It is a summit changing by meters in days. It is a volcanic structure unstable enough to produce both eruption products and collapse. It is a machine that can alter its own resonant plumbing while it runs. The hardest part still remains unresolved. Researchers do not have one universally pinned-down mechanism for every harmonic tremor episode at NOAA. It could be magma movement, it could be gas release, it could be eruption pulses driving resonance in cracks or conduits. It could be a combination that shifts from one episode to the next. But uncertainty at that level is not the same as not knowing what class of thing made the sound. The source does not need a monster photo. It needs repeated detections, a plausible location, the right spectral pattern, and a seafloor restless enough to match. So the answer to how a volcano can be heard before it is seen is dry but solid. First, the hydrophones catch a sustained harmonic tremor. Later, the maps show a summit near the sea surface rebuilding and collapsing in real time. The sound came first. Then the seabed changed by 18.8 meters in 5 days, under 100 meters of water, while the spectrogram kept drawing those thin, parallel lines. Number 2. The background roar. The seafloor can change before anyone sees it, but the hydrophones recording that change are never listening to an empty ocean. They are listening through a permanent layer of engines, propellers, hulls, and distant explosions. In the early 1990s, NOAA scientist Christopher Fox and his colleagues at the Pacific Marine Environmental Laboratory began turning Cold War surveillance into a scientific listening system. The Navy had built SOSUS to detect submarines. Now, its hydrophones were being used to track earthquakes, volcanic eruptions, drifting ice, whales, and sounds no one could immediately name. That created a strange problem. Better hydrophones gave scientists more detail, more range, and more detections. They did not always produce clearer answers. The ocean was becoming easier to hear and harder to interpret. By 1995, parts of the Navy's listening infrastructure had been declassified for civilian research. The sensors could detect a low-frequency signal across enormous distances, but every recording carried the same hidden burden. The ocean had a noise floor. Below about 300 hertz, commercial shipping was one of its dominant human sources. Hundreds of thousands of engines and propellers were adding a deep, continuous rumble to the water. A ship does not need to be close to be heard. Engine vibration enters the hull. Propeller blades push against the water, creating pressure changes that can travel through the deep ocean. In the right acoustic conditions, the sound can move across an entire basin while the ship remains far beyond the horizon. The traffic was growing too. In shipping-dominated bands off California, researchers found that low-frequency ambient noise had risen by roughly 10 to 12 decibels between the 1960s and the early 2000s. That is not a small adjustment on a volume dial. A 10 decibel increase represents about 10 times more acoustic intensity. It can bury the low rumble of a distant whale call, leaving researchers unable to prove whether a quiet biological signal was absent or simply overwhelmed. The sea had acquired a man-made bass note. That was the sound swallowing the others. Ships do not produce one clean tone. Their sounds overlap. Engines pulse at different rates, propellers cavitate, steel vibrates, waves scatter the signal. One vessel may be faint, but a shipping lane can become a moving wall of sound stretching for hundreds of miles. Scientists face the same masking effect when they investigate unexplained sounds. A weak biological call can resemble background machinery. A small geological event can vanish beneath shipping noise. A hydrophone may record a powerful waveform without showing whether it came from one extraordinary source or many ordinary ones layered together. Imagine a researcher reviewing a trace from a remote station. A sharp pulse rises above the shipping band, followed by a faint, repeating pattern below 300 hertz. The pulse has the timing of a geological event. The lower pattern could be a whale, propeller modulation, or an artifact of the propagation path. The ship tracking log shows traffic nearby, but not enough to identify a single source with confidence. The researcher can mark the pulse as detected. Weaker pattern must remain unclassified, because assigning it to a whale would turn a possibility into evidence the recording cannot support. The famous unexplained sounds were never heard in silence. The Bloop, Julia, Slowdown, and the other celebrated signals came through observing systems shaped by military listening stations, shipping routes, seasonal ice, and the physics of deep ocean propagation. What counted as unusual depended partly on what the network could separate from everything already present. The background was not merely interference. It became part of the evidence. A natural event can be identified by its timing, frequency, direction, and repetition. Those clues weaken when the surrounding noise rises. A source may be real and still look uncertain because the recording contains too little contrast. The mystery is not always that the signal is strange. Sometimes the signal is faint. Another sound enters the ocean. Not a constant roar, but a repeated impact. Marine seismic surveys use airgun arrays that fire about every 10 to 15 seconds. Each blast sends a sharp pressure pulse downward, through the seafloor, and outward through the water. The survey vessel moves, but the interval stays steady. Across a listening station, the result can resemble a metronome crossing the basin. That rhythm can overwrite a weaker natural pattern. A fault tremor or animal call arriving between blasts may be mistaken for noise because the strongest repeated trace dictates the shape of the record. The pattern is easier to recognize than many natural sounds because it repeats with machine-like discipline. Recognition does not guarantee visibility. Hydrophone may reveal the pulse long before anyone knows exactly which vessel produced it, where the array was positioned, or what smaller signals were buried beneath the sequence. You are listening at the bottom of the ocean. A whale calls somewhere beyond the horizon. A fault slips beneath the seabed. A ship passes hundreds of miles away. The hydrophone receives all three, but the strongest source dominates the recording. The weak signal does not vanish from the ocean. It vanishes from the explanation. The question is whether the detection preserves enough information to prove what made it. A 10 decibel rise in intensity can leave the waveform present while removing the comparison researchers need: a clean interval, a stable frequency, or a direction that separates one source from another. The background changes with traffic, weather, season, and geography. A hydrophone near a shipping corridor hears a different ocean from one placed beneath a remote stretch of the Pacific. A signal recorded once may be impossible to classify. The same signal repeated at the same location, in the same season, with the same acoustic shape, becomes a different kind of evidence. Long-term listening gives scientists a way to build that evidence. Old Navy recordings can be compared with modern measurements. Shipping patterns can be mapped. Seismic surveys can be logged. Whale calls can be matched to tagged animals. The noise floor shows what the ocean has been doing around the signal, and which comparisons are still possible. It also imposes a limit that no new sensor can automatically solve. A more sensitive hydrophone can detect weaker sounds, yet detection is only the first step. The ocean around the signal is louder. The source may remain hidden inside a larger acoustic crowd. Commercial shipping has changed the conditions under which every other sound must be heard. Somewhere in the archive may be a low-frequency biological call, or a small volcanic warning that was recorded but never recognized. If its trace fell below the noise floor during the only moment it occurred, no later analysis can recover the distinction. Number 1. The Bloop. In 1997, somewhere in the remote South Pacific, a signal rose out of the darkness and crossed an ocean basin before anyone could see what made it. NOAA hydrophones linked to the old SOSUS network recorded it. The system had been built to listen for submarines. By then, scientists also used it to hear earthquakes, volcanoes, whales, and ice. The sound lasted roughly a minute. Its frequency climbed rapidly. It seemed almost biological. No sailor heard a creature calling beneath the waves. No camera captured a shape. What existed was a pattern, copied by instruments separated by more than 5,000 kilometers. The red peak that made everyone imagine a mouth. A sound can become famous before its source is visible. The ocean carries pressure farther than sight can travel. Hydrophones detected the bloop across the Pacific, proving that the event was powerful. Power, however, is not identity. A signal can be enormous and still leave behind only a question shaped like a waveform. The recordings came from NOAA's Pacific Marine Environmental Laboratory. Analysts were listening through a network descended from the United States Navy's sound surveillance system. SOSUS had been designed during the Cold War to track submarines moving through deep water. Its hydrophones were spread across vast distances and connected by the ocean's unusual physics. Low-frequency sound can enter deep channels and travel for thousands of kilometers with surprisingly little loss. By 1997, that listening architecture had become a scientific instrument. It could register the tremor of a submarine volcano, the fracture of an earthquake, or the low pulse of a whale moving beyond the horizon. Bloop appeared, it did not fit comfortably into any familiar category. The estimated source lay near 50 degrees south and 100 degrees west, far out in the South Pacific, west of southern South America. The area was remote enough to invite almost any explanation. No nearby ships pointed to an obvious source. No known eruption was waiting there. No animal was known to produce a call with that combination of intensity and range. The signal rose in frequency over about a minute. Played back for human ears, it sounded alive. A low, swelling cry that tightened as it climbed. The profile suggested a biological source, but suggestion is not evidence. A signal can sound organic without revealing whether it came from lungs, fins, rock, or ice. The name did not help. NOAA used informal labels for unidentified sounds, including Julia, train, upsweep, and whistle. Bloop was unusually easy to repeat. It turned a technical anomaly into a character. The sound became a creature before the data had finished describing it. Online retellings widened the gap. Some versions treated the bloop as proof of a giant animal hidden in the deepest part of the Pacific. The logic was simple. If a whale-like sound traveled more than 5,000 kilometers, the animal must have been larger than anything known. The hydrophones were not measuring an animal's size. They were measuring acoustic energy after it had moved through a complicated ocean. Temperature layers bend sound. Depth changes its path. Seafloor structure affects propagation. A powerful event can travel unusually far without coming from a living body of impossible scale. The bloop was not merely loud, it was locatable. Multiple arrays heard it at different times, allowing researchers to estimate where the pressure wave began. A broader detection network made the source region easier to narrow. The mystery survived because one kind of knowledge arrived before another. The instruments knew where to look. They did not yet know what they were looking at. NOAA researchers eventually compared the bloop with signals recorded near Antarctica. Large pieces of ice produce their own acoustic signatures when they crack, fracture, scrape, or separate from a glacier. An iceberg calving into the ocean can release enormous energy. A fracture can send a sharp, low-frequency disturbance through the water. To human ears, the result may sound organic. Its mechanism can still be geological and physical. The comparison changed the mystery's shape. The bloop's rising frequency, its extraordinary range, and its estimated South Pacific origin were no longer isolated clues. Together, they matched the broader acoustic behavior of icequakes. NOAA's official attribution was cracking or fracturing ice, likely associated with a large Antarctic ice event, not a monster. The explanation did not identify one named iceberg or produce a photograph of the exact fracture. It established the class of source more clearly than the individual event. Ocean evidence often works this way. It can identify the process while leaving the moment itself unobserved. The recording came from 1997. The source region lay thousands of kilometers from the nearest audience. No visual scene waited at the end of the trail. The public story asked what creature could have made the sound. Hydroacoustic record asked a narrower question. What physical event produces this profile, at this range, in this part of the ocean? The narrower question is harder to sensationalize. It is also closer to proof. Location limits the possibilities. Range measures the event's reach. Acoustic profile reveals how the signal changed as it traveled. Later icequake recordings provide the comparison the original moment lacked. None of these clues is decisive alone. Together, they replace an imagined animal with an attribution supported by physics. A signal can cross an ocean basin before anyone sees its source. Proof does not require a monster photograph. It requires independent constraints that survive the distance. Where the signal began, how far it traveled, what shape it carried, and whether later events reproduced the same signature. The bloop was never a creature waiting beneath the Pacific. It was an icequake heard through an ocean-wide listening system and transformed by distance into folklore. The waveform outlived the fracture that created it. Long after the ice broke and the water went still, the evidence kept moving through archives, speakers, and human imagination. The ocean offered no face. It offered a location, a range, a pattern, and finally a physical explanation. Proof looked like that in the dark.